Hey everyone. So today we're going to be talking about how to translate different kinds of graphs for kinematics, right? So the three graphs you'll see in front of you are a position, velocity, and acceleration versus time graph, right? All of them are going to have time as the x-axis, right? So I'm going to go ahead and here and label them all t here, just so that we're clear. Right, so we have the first one is going to be displacement, the second one is velocity, and the last one is going to be acceleration. Right, so we're going to graph the change versus time for all of these different values. And usually when we do this kind of problem, we'll be given one of the graphs and asked to find the other ones. In this case, and which is the most common scenario, we'll be given the velocity graph. Right. So there's a couple things to be aware of when translating the graphs, and we'll go over them now before we start actually doing it. Right? The first thing is that when you have a positive velocity, right, the object is moving, let's say, in the forward direction, right? So we're going to have to distinguish a forward and backward direction. Let's say the forward direction is positive and backwards is negative, right? When the object has a positive velocity, that means that its position will be increasing, right? So let's say you have a positive. Let's say you're starting at this position here that I'm outlining in the position graph, and your velocity is positive. That means sometime later your position will be here, right? It will increase. There will be a net change. Your delta x will be positive, right? On the other hand, if your velocity is negative, right? So if you have a velocity here, like I'm pointing out in the velocity graph there, if you have some value that's negative, then your delta x will be negative, right? So if you were to start here, you'll end up here, and this delta x here will be negative, right? And then, of course, if your velocity is 0, so some scenario like that region there, you will have no change in position. So if you start here, you will end up here. There will be no change in position, right? If your velocity is increasing, right? So if your velocity is increasing, let's say that region there, right? Then your position function will be concave up, right? So it will look like this. The reason being that if the velocity is increasing, the rate at which you are changing position is increasing. So while at the beginning you're starting off and your rate of change, your slope is small, as you get up here, your slope is larger, right? Because remember, velocity is the slope of a position graph, just like acceleration is the slope of a velocity graph. If you're taking calculus or you're taking it now, that'll be familiar to you, right? So then the opposite is true. If you're here, let's look at this region. If your velocity is decreasing, that means your position function will be concave down, right? Your slope will be decreasing, right? Because remember, velocity position is the slope of position. So velocity decreasing, slope is decreasing. It's approaching 0. Right? And then the reverse is true for acceleration. So, or not actually the reverse is true, but it won't be curved. So acceleration will exhibit a straight line behavior. So let's say look at this region here. So here the velocity is increasing, that means acceleration is going to be positive, right? If we look at this region here, velocity is not changing, so our acceleration will also be 0. Now what about this region here? Velocity is not changing, but it's non-zero, right? Acceleration is still 0, right? What about this region? In this region, the velocity is negative and becoming more positive. So we would think, oh, acceleration might be negative, right? Because we're slowing down. But that's not actually true. The acceleration will only be negative if you're slowing down if the velocity is positive. In this case, since velocity is negative, your acceleration will actually be positive to slow down. And here, for this region, right, since you're accelerating in the negative direction, your acceleration will be negative, right? And when we do the acceleration graph, you'll see that we do these little like dashed lines to designate the different regions. So you'll see something like this, maybe, right? And the reason is that we're assuming that the acceleration occurs instantaneously, right? We see these sharp breaks in the graph. I'm erasing all the arrows here. So we see all these sharp breaks in the graph, right? So like this region, this region. We're not seeing like smooth curves, because that would imply that the acceleration changes. And when we do kinematics, we only care about constant acceleration, right? So let's go ahead and draw the graphs, and then we'll go over some of the points. So let's do the position graph first. So here in region AB, you have a positive acceleration, and your velocity is increasing, so you're going to see something like this, right? So you see it's a slope that's increasing, and then we're going to be constant velocity, right, for a while, so we're going to see something like this. All right, let me actually draw that a little bit shallower. Right? And we try when we draw it, it's difficult, but we try to match the slope here. So right, so the slope here should be equal to the slope right there at the beginning, because in theory the slope is no longer changing since velocity is constant, right? And then here, right from C to D, your slope is going to approach 0. So let's and I've reached the border of my drawing capability. So I'm going to undo this a little bit just so I can get the right shape. Draw this a little bit shorter. Right. So this region here is still constant velocity. This region here, you'll notice, is I tried to do my best to draw it concave down within the space region. You see how it flattens out and then it approaches a 0 slope right at that point there. And then we're at constant velocity for a while. We're actually at 0, which means our position will not change from D to E, right? So it will be constant there. And then F will actually start to increase downward. So from E to F, we'll increase our velocity, right? Our slope is becoming more eccentric. I'm going to try to draw a little bit shallower. Right, so that's F, where you see how our slope is starting to come back down. And then from F to G, we're at a constant negative velocity, and we'll be moving like that. And then from G to H, we'll be smoothing back out to a 0 velocity, right, back at H. So drawing these graphs can actually be pretty tricky, especially if you're doing it by hand, just kind of eyeballing it without values, because then it's like, how far do you really go, right? And you'll notice, for example, here versus here, the max velocity here will be greater than max v here at the bottom. Let's call this v2. So max v1 will be greater than v2, and that's not necessarily reflected here in this graph per se, right? Because BC does not really have a sharper slope than FG, right? So let's call this FG here. The slopes look about the same, right? When in reality, this velocity has a larger magnitude than this one based on the velocity graph. So that's something that's very hard to translate by hand, and if you have graph paper, that's much easier to convey, so I would recommend doing that if you have the option to, right? Otherwise, it's most important to get the general shape and get the concavity as best as possible, right? So I'm going to go ahead and erase this. Alright, now let's try the acceleration. This is pretty easy. So the acceleration. So here, the acceleration for AB is going to be positive, right? We're increasing velocity. Then we're going to be at 0 acceleration here. And then CD, we're going to have a negative acceleration because we're slowing down. We're approaching 0. And it's a positive velocity. From D to E, we're going to be 0 again. From E to F, we're going to have a negative acceleration, right? Because we're increasing speed in the negative direction. And I'm going to say it's about the same as the other one. And then here, actually, let's call it a little bit less just because the time interval looks about the same. And the change is less. And then FG, we're at 0 again. And then GH, we have a positive acceleration, which will be a little bit less than the previous one. Or positive because we're slowing down, but we're coming from the negative direction, right? So these will be the three graphs, more or less, that you'll see. Right, so we have position, velocity, and acceleration. The trick is to match the different slopes and the different rates as best as possible. Usually, it's mostly a matter of practice and visualizing and understanding what's going on. So if you see enough velocity graphs, you'll start to just kind of get the hang of it. Of it's a positive slope line. This is what the position graph should look like, right? And you kind of get the feel for it after a while. And it becomes second nature. But it is very important to practice because it is a very useful skill in terms of understanding what is actually happening when you do these kinematics problems, right? Notice, for example, that the only time the object actually moves backwards is in this region, whereas the velocity is negative, so it'll correspond to this area here, which does not necessarily mean a positive or negative velocity, right? Nor does it mean that a decreasing velocity has anything to do with a negative position. In fact, a negative acceleration, you can still be moving forward, right, as you see in this region here. So it's those sorts of relationships that these graphs help you become comfortable with. All right? That's it for this video. Next time we'll do some more problems, so stay tuned. Thank you. See you next time.